So I see some hands that were raised from before, from the end of Dave and Kelvin's talk. We'll start with you. So the first hand I have is from Javier.
Thank you very much for your talk. What I was wondering is that you are not using the model of cybernetics to try to explain the idea of consciousness that you are showing. Because basically, I think what I understand is that John von Neumann had a very strong relationship with Norbert Wiener and Shannon in that sense. So I was wondering that. So thanks.
Yeah, I don't think we intended to be bringing in anything specific to cybernetics. That said, we're certainly adopting, at least as our example of a mathematical theory of consciousness, Tononi's integrated information theory, which does have information at its center. It actually doesn't bring in Shannon's measures of information in a central role, but basically it's Tononi's integrated information as a network property defined in terms of certain network structures. So maybe that's you can see that as a broadly computational approach. Interestingly, Tononi himself resists the idea of consciousness, at least on standard AI systems, because he believes that computers with von Neumann architecture have zero phi due to the way they're set up. So parallel machines may be conscious, but systems with von Neumann architecture are not consciousness, according to Tononi. Personally, I think that's a defect in his theory, and it ought to be corrected. But anyway, the relationship between that approach and cybernetics is complicated.
Thank you. The next hand I have is from Arkadiusz.
Yeah. You said, when you mentioned super selection rules, that consciousness is kind of perhaps resistant to superposition, so it may be a super selection rules, but then you gave up because you said that super selection values cannot change, but this is not quite correct. Because to have super selection rules it's the same as to have a non-trivial center in the algebra of observables, the Boolean part, okay, that commutes with everything. And of course, it's invariant under automorphic dynamics, under unitary evolutions, but it's not true when you consider more general classes of evolutions, like completely positive semi-groups. And there are such models. I don't understand why you abandoned that idea.
I'm a little bit out of my depth here. I know that in the literature on super selection rules, there's some discussion of the loophole, whereby I don't know where the relevant I don't know if it's the relevant operator needn't be Hermitian or something.
No.
There are cases where you can get to.
No. It's just a question of coupling a classical system, because the consciousness being commuting with everything is a classical system. Classical system don't superpose with a quantum system, which is we need quantum mechanics, and we need quantum system, and we need to couple. And it is possible to couple classical system and quantum systems. There are such theories. I wrote a bunch of papers developing such theories, and they work perfectly. There is nothing wrong with that.
Okay, I need to read those papers, I think.
I will send you.
I think to the degree to which one is abandoning strict universally unitary evolution altogether, then the argument for not generalizing unitary evolution to other kinds of completely positive, time evolution are maybe less strong.
We have another article on this, by the way, which is called "Zeno goes to Copenhagen," where we try and raise this Zeno issue quite generally for a number of measurement style interpretations. And we are one of the options as a way out is what we call quantum classical dualism. There are quantum systems, there are classical systems, they have different dynamics, they interact in special ways. We just say we try to avoid that kind of quantum classical systems. All systems for us are quantum systems.
The question is, does Zeno ever make it to Copenhagen? So the next hand I have is Simon.
Right, yeah, thanks, David and Kelvin. I enjoyed your talk, and I did get a bit stuck with a couple of points, and can you just help me with them? So one point is, plants are IIT systems, and and so forth. But does that mean before the evolution of plants in the universe that there was only unitary evolution? And if so, how is it that the unitary evolution gave rise to something that could function as an IIT and so on and so forth? So that's, you must have an answer to that. And the other is that why are you in your IIT, are you building in already probability distributions? One might have thought, of course, in the literature that you're sort of leveraging off, that would be very normal. Why not? A great deal of the sort of dynamical systems they're interested in can be formulated as probabilistic systems, but in foundational studies in quantum mechanics, to have a sui generis form of probability coming in, I just don't know how that connects with the stochastic dynamics. But you've evidently solved that problem because you've actually worked out this model. So please tell me how. I would like to know.
Kelvin, you want to take this one?
Sure. So on the first point, you're right. In the early universe, it's as if we've got the Everett interpretation. And then you get some Q-shape developing in a given branch. Now you've got Q-shape differences. And so this slow continuous collapse begins. It can speed up if there's more complex Q-shapes in the different branches. But you're right, the universe starts out like the Everett interpretation. Collapse begins when there's a non-trivial Q-shape in a given branch. On the second point, this might be a good one to pass over to Johannes. So the question was, what are the nature of these probability distributions in quantum integrated information theory? And well, they're meant to be, looking at a system or looking at a subsystem. Given unit, correct me if I'm wrong, Johannes, but just given unitary dynamics without collapse, what is the contribution of a given subsystem to the probability of a later state? Is that on the right track, Johannes? Can you?
I'm not sure which probabilities you exactly refer to, Simon.
Well, when you first started to sketch the simplest of all models, I think you just had a two-state system, and you had certain probability distributions relating the two. Those
that was classical IT.
Right, indeed. So how did that model and how did the probabilities in that model get to be implemented in a quantum mechanical way?
Yeah, so how it works is that basically, so they propose the theory in classical terms, and you can then analyze the theory and you can see what exactly does it presuppose on a system end. And that's quite general, like decompositions of systems, you need to know how these go, and a few other things. And then you see that the sort of the system class, they single out as the one which you can plug into the formalism. That's just satisfied by quantum systems as well, if you do the mathematics precise. And then what were the probability distributions in classical states are just the density matrices in the quantum case. So there are no like probabilities in quantum IIT. They only come in sort of because of the collapse dynamics.
Right. So you're, as it were, getting to a quantum system to implement this previously classically modeled IIT using probability distributions on some other interpretation, whatever, that's the other literature that you're looking at. But then could that be implemented in the sense using quantum probabilities in a dynamical collapse mechanism? Is that correct?
As far as I understood, yes, but I'm not sure if I understood all details.
Yeah. I mean, just the other thought I did have, there have been people who didn't mention Donald Page, for example, and Matthew Donald, people who have worked out mathematical models relating to interpretation of quantum mechanics. Don Page, of course, in the case of the Everett interpretation or something like. Matthew Donald, I'm not so sure, but you're familiar with this literature?
Once upon a time, I had long email correspondences with Don Page about all this, but I'd have to go back and look it up to refamiliarize myself.
Okay, so he's still keen on it, so it might be worth connecting with him.
All right, I have two more immediate questions, I think, for Dave and Kelvin, and then I'll go back and start calling on people who had questions from previous talks. So the two questions that I have are Jerome and Adam. Jerome, please go ahead.
Hi, wonderful talk, really enjoyed it. I had some, I guess, general metaphysical sorts of questions about the relationship between Q-shape and consciousness. In a paper, it seemed to be described as a physical correlate. Now, is this merely a sort of supervenient correlate or an identity relation? And I think this might have some significance in whether or not it's consciousness that collapse is the wave function, or maybe just physical facts about the Q shape itself as, what's doing these sort of collapsing. And if you could expand upon that here.
Yeah, I think we mean it to be consistent with both. I mean, the beauty of the neural correlate of consciousness program in neuroscience is this notion of a correlate is meant to be neutral between, say, a strict identity between a neural state and consciousness, or some kind of correlation or supervenience. It's certainly most straightforward on the materialist approach, where consciousness is identical to its physical correlate. The physical correlate will resist superposition. Consciousness will resist superposition. Those will basically be the same thing. But on a property dualist version, which I'm most sympathetic to myself, then there'll be psychophysical laws connecting the physical correlate of consciousness with consciousness itself. You'll still have supervenience, but it will be nomological in virtue of this law, rather than the kind of metaphysical relation you'll get from a strict identity. And that does raise the question that you raised: what is the causal role of consciousness here? You might think, the PCC, the physical correlate of consciousness, is doing all the work. So it's very important on our picture that the fundamental, the fundamental principle here is that consciousness itself resists superposition. And then there'll be this psychophysical law saying that roughly a phenomenal Q shape embedded in consciousness, always is strictly tied nomologically to a physical Q shape, one of these network properties. These two have to move in lockstep, so that the super resistance of consciousness leads to super resistance of the PCC, and thereby leads to brings about the various results, like actions, which are results of the collapse of the PCC. So that's our way to try to bring in a causal role for consciousness in this picture. I think it's a reasonable issue to ask: is that all the causal role of? Do we want a stronger causal role for consciousness than that? But at least at the moment, that's the best we can do in this framework.
So we have time for a quick follow-up question there. So then it seems like what you would want to do is find a way maybe to demonstrate that nothing about the Q shape itself and the physical system is capable of giving a explanation for the collapse, right? Such that we have to appeal to maybe the consciousness itself rather than physical facts about the Q shape. Correct?
Unfortunately, right now, it looks like we're going to have empirically equivalent theories where the Q shape does the collapsing, and Q shape is correlated with consciousness, which does the collapsing. So it's not clear to us right now that there's a relevant empirical test there. I mean, there's weird stuff that could happen where consciousness somehow gets autonomous, but that's, I think, goes to a more radical form of dualism than we're happy with. But it is an interesting question to think about. Yeah, more radical versions of a theory that might be open to that kind of stronger empirical test.
Thank you.
I saw briefly a hand from Adam. Adam, do you still have a question?
Yes, I do. Sorry, yeah, I took my hand down because I wanted to make sure I didn't forget to, remove my hand from the screen thing after. Anyway, yeah, I have a question about what Kelvin said. Just thinking through the answer you gave Simon about how, Q-shape things would show up in a branch, and then that would lead to, the universe going from a many worlds like thing to this other view. Wouldn't that mean that the odds of consciousness of some kind, even at the level of plants, showing up at some point in the universe would be 100%? If it's physically possible for some system with the right properties to show up, wouldn't that mean that the odds of such a system developing in one of the branches be 1? Not that that's a problem, just it's weird.
It does sound weird when you put it like that.
Yeah.
I don't think it's true.
Sorry?
I don't think it's true that the probability is 1, because you can very frequently, most times when consciousness evolves in a branch, it will collapse back into a state of 0 consciousness. You're going to have to be very lucky for it to, a low amplitude branch with some consciousness will evolve, and most of the time it'll snap back to 0 consciousness, but maybe once in one branch, you'll get lucky. It'll go to some consciousness, which will stick around.
Okay.
That's
Interesting.
hard to get going, but you might think given enough time, it's inevitable.
Yeah.
Almost a Boltzmann brain type like argument.
Yeah, it's definitely not a problem. It's just weird. Good. Okay. Thank you. That's all.
It'd be great if it turns out consciousness is inevitable. Then we'll have it as this like teleological force. Every universe has to collapse eventually.
Good. Thanks.
So I want to go, I know there are a couple more hands maybe about this discussion. I would like to give people a chance who had questions from the earlier ones, but I did have a super, I think, quick question that maybe could just be answered in the chat. But I frequently hear that von Neumann is brought up in these discussions about consciousness being related to collapse, along with Wigner. But I've never been able to find, and I know that Dave was very careful to say that it wasn't maybe a definitive statement from von Neumann, that maybe it was just sort of a more subtle connection. But if anyone does have a reference they could put in the chat where von Neumann takes a clearer stand on this, because most people point to like, his treatise, the mathematical foundations of quantum mechanics. He definitely does not make a claim like that there. So I'm just curious if anyone has a stronger reference.
Can I just say something about that?
Oh, sure.
Yeah. So in the mathematical foundations of quantum mechanics, not only does he not say that, it's incompatible with what he says, because it's very important to the to this principle of psychophysical parallelism that it doesn't matter where you put the
exactly. When he's very clear, you should be able to put the code wherever you want. Yeah.
Like a couple of years ago, I spent some time trying to trace the history of that attribution to von Neumann, and I think that is that I think it just stems from a misreading of the passage in Mathematical Foundations.
It seems like a very non-von Neumann attitude to take.
Indeed.
Yeah. So I was
so
very curious.
I think that, so maybe someone else might be able to say anything, but my conclusion is that it can be traced to just simply a misreading and a conflation of Wigner and von Neumann.
We do have a footnote about this in the paper, which I'll read. It's clear that von Neumann endorses a measurement collapse interpretation, and he says that subjective perception is, quote, related to measurement, but he does not clearly identify measurement with conscious perception. In his discussion of observed systems, 1, measuring instruments 2, and the actual observer 3, he says the boundary can just as well be drawn between 1 and 2 plus 3 as between 1 plus 2 and 3. That suggests neutrality on whether the collapse process is triggered by measuring devices or by conscious observers. He also says the boundary is arbitrary to a very large extent, which is not easy to reconcile with the fact that different locations for collapse are empirically distinguishable in principle, blah, blah, blah.
That's because he didn't think collapse was a physical process.
That was my read also. That what he was saying was that it's like a gauge freedom. You can put the line wherever you want. Not that it fundamentally happens at some place, we just don't know. But the fact that we can put it anywhere is a sign that it's not really a physical thing that's happening. Yeah, maybe I'm just misreading it.
On this reading, does von Neumann have an interpretation?
What's that?
On this reading, does von Neumann have an interpretation?
He does. He's very non-committal in the book.
Yeah. Yes, the question is whether what he says is something we should be satisfied with. But I think that Jacob is absolutely right that he doesn't think of collapse as a physical process. It's something, at a certain point, we decide to make the cut and select one of the results. And that's actually very similar to what Heisenberg says too. And it sounds like very Copenhagen-y, and so whether that amounts to an actual interpretation of quantum mechanics or not, good question.
Interpretation or not, what is he going to say to the fact that different locations for the cut are in fact empirically distinguishable in principle?
He doesn't address that, but I think that,
it's not mentioned in the book that I can tell.
It's not mentioned, but I think I know what he should say. It is Bell in one of his papers said that the rule of thumb that seems to be employed by practicing physicists is include as much in the quantum system, included as much in the quantum system so that pushing the cut back further won't make any difference. So, right. And I think both Heisenberg and von Neumann are at least implicitly employing that rule of thumb. That there's a certain amount of arbitrariness to where you put the cut, but if you put it too soon, you're going to run into trouble. So find a place to put it where you can push it back further. And it doesn't make a difference.
That sounds like a potential argument for putting the cut just next to consciousness, because push it back into from little systems to big systems to brain to consciousness, push it further than consciousness, and then you suddenly get into Everett territory of superposed observations. But that's at least sounds like a pragmatic argument for consciousness as a locus of collapse.
Simon, do you want to? I think you had a comment you wanted to add to this.
Thank you. If I could just jump in. I mean,
yes,
one point to make is that I think that there's a very consistent reading of von Neumann as essentially an Everettian, but I won't try to push that line. But the other point is that von Neumann is known to have been extremely interested and encouraging of the work of London and Bauer. And I think that there was no question that he was engaged and interested in this whole potential interplay between mind and physics. And after all, his subsequent focus on computing, theory of computation, and so forth is evidence to that. So, Wayne, do you have comment?
Yeah, I mean, I think that London and Bauer, what they say in that paper is at least intended to be consistent with what von Neumann says. So, like, for them, it's it's a matter of like. It's not a physical collapse induced by consciousness. It's that, okay, when we become aware of the result, then we select one from the other. So Wigner quotes London and Bauer and says that consciousness is related to collapse, but they aren't making the Wigner proposal that consciousness is playing a causal role in a physical collapse. I think if you read them carefully, that's not the case. And actually, and Wigner also is not attributing that to them. Yeah.
No, I agree with that.
It is a very unfortunate fact of history that von Neumann died in 1957, which was the year that is usually associated with Everett's suggesting of the relative state. So there's some of this we just can't know, unfortunately. All right, I'm sorry this was supposed to have been a super quick question. I didn't mean to divert us on this tangent. We do have a number of questions from before I'd like to get to.
May I ask David one more question?
Related to this?
Yes.
Yes, go ahead, please.
That's about, when you speak about consciousness, do you mean subjective consciousness or it's something objective? Like you remember Wheeler, right? Saying where he said, okay, you have to observe, right? And then, then he withdraw. No, it's not subjective. But so what about your point?
A lot is going to depend on what you mean by subjective and objective. I would say that consciousness is a state of subjective experience by definition. It involves what it is like to be a given subject at a time. However, I think there are objective facts about subjective experience. It's a matter of objective fact, whether somebody's experiencing, say, a subjective pain state at a given time or not. So subjective in one sense, objective in another sense.
But is it a person who collapses the wave function?
It needn't be a person, I think. I think ants are conscious. Ants may well be conscious, and they are, I don't think they're people. But is it a subjective experience? It's states of a subjective experience that collapses the wave function. And in my view, any consciousness is had by a subjective experience, although I don't think that needs to be a person in the standard sense.
All right, so we had a question back from Vanessa's talk. Sebastian, are you still here?
Yes, thank you.
Please go ahead.
I have a comment and a question about the Vanessa's talk about molecular structure. In my opinion, there are two things that seems similar, but they are different. On one hand, there is the measurement problem, which tries to explain why measuring devices show a definite values when the state.
Sorry there, Sebastian, you're muted. Do you want to unmute?
Now?
Sorry about that. Yeah, go ahead.
Did you hear the first part?
We just lost the last sentence or so. Please go ahead.
Okay. On one hand, we have the measurement problem, which tries to explain why measuring devices shows definite values when the state of the system is a superposition. This is the measurement problem. And in the other hand, there is the molecular structure problem, which try to explain how to recover the molecular structure from quantum mechanics. So I believe that it is possible to solve one problem, but not the other. For example, in the case of chirality, the different solutions explain why we can see chirality with our apparatus, and these solutions usually takes into account that there is no isolate molecules, but they consider an environment. And it works, but these solutions recover the definite values of the apparatus, but not the molecular structure. So, for example, in the Logan example, where there is a molecule in interaction with its environment, maybe the conclusion is that the molecular structure in an isolate molecule does not exist. So this conclusion is a negation of the molecular structure, not a reduction. So in this sense, we can say that with quantum mechanics, we cannot reduce the concept of molecular structure to quantum physics. So I want to know if you are in agreement with this or not.
Yes, should I take this up? Or yeah, thanks a lot. Yes, this is a question that I've been asked before. I don't agree completely with the way you've put it. As I understand it, the point is here that even if we could resolve the measurement problem, and even if we could measure by quantum mechanics, you know, the property of being either left or right-handed through the Schrödinger equation, even then, it wouldn't be enough to say that molecular structure is reduced by quantum mechanics. So it seems here that you're suggesting that even if we identify this property, chirality, through quantum mechanics by resolving the measurement problem, molecular structure is still not reduced. And to an extent, I am sympathetic. I understand this point, but nevertheless, I have some objections in the sense that molecular structure is not an all or nothing property, right? So it is a collective term that refers to more than one properties. So when you describe the structure of a molecule, you have to identify whether it is a chiral molecule and what sort of chirality it has, what kind of bond length it has, the angles between the bonds, how the atoms are situated with respect to each other, right? So it's a collective term that refers to identifying more than one properties. And in that sense, I agree with you. Even if I get chirality, I don't get the entire structure of the molecule by quantum mechanics. Nevertheless, I don't see why not quantum mechanics couldn't derive each and every property that is necessary in order to form a complete description of molecular structure quantum mechanically. So if that's what you mean by this question, then I think this is my answer to it. Hopefully,
yes,
I've understood.
Related, but I want to consider that maybe you can explain some properties, but in quantum mechanics, there are incompatible properties. So if you claim that you can get the position and velocity, for example, of the atomic nuclei, you are entering in a contradiction. So
yeah, so but still, doesn't this have to do with how you interpret quantum mechanics? So Heisenberg's uncertainty principle and how we understand Heisenberg's uncertainty principle is part of the story that we give through quantum mechanics. No, maybe I'm misunderstanding something here, but that's how I would see it, at least. I see Alex has a finger on this.
Yeah, Alex, please go ahead.
Thanks. No, I just wanted to make the point that there are classical descriptions given of kind of molecular structure, and it would be a mistake to attempt to recover all of the details of what we might think of as a classical idealization. So each individual molecule having a perfectly well-defined position and being perfectly stationary and such like. What we can recover, as is standard in kind of cases of intertheoretic reduction, is a very good approximation to that. So if what we're doing is affecting something like a quantum mechanical reduction of chemical structure or molecular structure, we shouldn't hold ourselves to recovering the exact classical idealized molecule in isolation. We should be doing something a little bit more of an approximation to that. I think that might help out with these kind of issues where people say Heisenberg's uncertainty principle will prevent one from getting the kind of classical molecular structure.
Okay, thank you for the answer.
Thanks, Vanessa and Alex. The next hand I have is from, and I know that Marian had a question all the way back from Lev's talk. I don't know if that's still the question you have, but feel free, Marian, go ahead.
Yeah, but I have also a question, probably some remark concerning reductionist, because you cited Dirac, that finally beautiful, quantum formalism is very powerful, but exact results are rare. And when you want to describe complicated systems, we have to use some approximations and phenomenological, quasi-phenomenological models. And it even happens in a standard model. What we have beautiful theory of QCD dynamics between quarks and gluons, but to describe something about scattering, we have to input some phenomenological parton functions and after treat hydrolyzation and things like this and put things by hand. So I am quite surprised that many people here believe that quantum mechanics will explain everything, starting from Big Bang up to consciousness and things like this, and everything has to be reduced to quantum mechanics, but probably is completely wrong. Quantum mechanics this is very effective to describe different phenomena which were in a domain which it was created. It's not necessary. We have to reduce everything to it and we'll be successful. And also, when I'm coming to Beck, I made a Beck comment about Lev is not here, Vaidman, but he knows my opinion about his.
Lev is here.
What? He's here?
Lev is here, but muted. Here, but muted.
Okay, no, probably he's sleeping. He is Israel. What time is in Israel? It's very late. Yeah. Anyway, but I want to tell you everything. What is my point of view? We know that when we look on experiences in quantum mechanics, we look on, in fact, in some kind of random experiments. We have some preparation, and after we have some black box, and we have outcomes. And what quantum mechanics give us, according to Boll and Copenhagen, some rules which allow us to calculate probabilities. But probabilities are not ontological things. They're objective characteristics of random experiments, but they are not properties of a coin when we are throwing. No, the flipping device. They're in some sense properties, objective properties of the random experiment. So talking about the tiger wave function of tiger of universe in my philosophy is very far-fetched. So for me, why I was claiming that if you are going to set this kind mix of statistical and Bohr interpretation of quantum mechanics, what is a collapse? So finally, you have destructive experiments in which we have outcomes and we have statistics, but we can have non-destructive, let us say, measurements that we get some. We transform initial ensemble of states, which we study, to another ensemble of states, and reduced wave function simply will help us to describe what happens to this new ensemble of states. So it is not physical process. It is simply passage from the description of the initial prepared ensemble to the another prepared ensemble after this non-destructive measurement. So you see, in this case, with this, I hope for Bohr and many other one-word physicists, there is no measurement problem. Instead of measurements, we have quantum phenomena and quantum experiences in which we have the interaction between measuring instruments and atomic objects. Wave function describes neither a single physical system nor the universe. This is what I wrote. What I also, about when we talk about human conscious observer, what qubits and qubits, which I also is against this type of interpretation of quantum mechanics. I was asking Chris Fuchs very many times. So imagine, we know that when protons collide, you can obtain different outcomes with some different probabilities, which we observe here. But if they collided before human beings were here somewhere in a cosmic rays, there were also some regularities what they were producing. And these regularities were some kind rules of laws of nature, which finally quantum mechanics could explain. So has nothing to do with conscious, in my philosophy, is with a conscious observer. So this is my philosophy, which I wanted to share with you. Yeah.
So I don't know if
it's too many. Yeah, I thought too many. It's yeah. Okay. Yeah, you are here. Okay, good.
Lev, you're welcome to reply.
Okay.
The issue of probability, I don't want to reply in detail. I invite you to come to the conference on Everett, and I will. I plan to talk more about probabilities there. About tiger, most of the tiger which I considered was first classical tiger and then classical tiger of a single world universe. So there was no question. We didn't have many tigers. And then I showed two tigers, one in superposition and not in really in transparency half on the other one. So I don't think you, in one word you could see it. But I made an experiment, and I have a good reason to believe that you also split and had another explanation of interaction-free measurement. My reason for this is that if not, then we need action at a distance and randomness in nature, which I think it's negative property. What evidence do you have that you didn't hear in parallel world my explanation of interaction-free measurement?
I didn't know what we were talking about because you skipped it. You've been talking only about teleportation, as I remember.
No, I performed. I invite you to do after the maybe or even now. Go to my homepage. There is a word splitter.
Okay.
I applied the word splitter. It's really connected to really random quantum device, and it split the word. And ask my word splitter which lecture to give. And then the word splitter told me, talk about teleportation. I'm sure, I'm confident that in parallel world, it told me to talk about interaction-free measurement. So I'm sure that I gave another talk in parallel worlds and you had another parallel world. And I think I have a good physical reason for this. I believe in it not because of David Lewis or any philosophical reasons. I want nice, clean physics. Physics without action at a distance and physics without randomness. This is, and I don't have any experimental evidence that I am wrong. So do you have any evidence or any reasons why
no, but Lev, fathers of quantum mechanics and Ballantyne, which is statistical interpretation of quantum mechanics proponent, never told about action at the distance. Nobody believed, they didn't believe that there is action in the distance, and there is no action in the distance. This I deeply believe there is no action. You don't need it. Let perhaps other people ask
maybe
questions.
just
we're going to have
what I am saying
yeah.
that for me, I wanted to explain the wave function is not ontological object for me. You know, so
we're going to have to pause. Lev, you want to say one last thing? We'll have to pause this and move on so we have time for other questions.
Yeah, okay. Thank you.
You're welcome. So, Lev, did you want to quickly say something, or should we move on?
No, I really wanted to say the action at a distance is very important. This is the reason why I believe in many worlds. And there is a real action at a distance. If we have an EPR pair, I think most of us believe that if we prepare two photons in EPR pair, they're really kind of EPR pair. Then this one of the particle in EPR pair is kind of real. You can, whatever I say, it's a wave function. You can say whatever you want to say. The reality of this, that you are ready to bet 50-50 that it will be up or down. Because you know it's entangled, and you know that probability, there is a real issue, whatever you want to interpret it. And let's say the one of the EPR pair, now it's in the moon. And now I say that we arrange a game or bet on a measurement which will be performed on this one of the particles of EPR pair on a moon. And I say that I can influence, change it immediately, faster than 1 second. Because we make a bet on what will happen to the moon. Later, people will come to us and will say what is the result, and we can put money. Now I have the other part of the EPR pair. If you playing against me see that I don't touch it, you should agree to play the game because you know it's 50%. If you see that I measured one, now you will not agree to play this. Therefore, definitely something on the moon changed immediately, because before you was ready to play and now you are not ready to play about an experiment which will happen locally in particular time in the moon. This is action at a distance. And if you don't believe in many worlds, there is no way to avoid this. Collapse, all the collapse, GRW collapse or Van Neumann collapse or any collapse, they all have this action at a distance. If I perform measurement on one of them, the wave function will be collapsed on the other thing. And even if I'm just a whatever cubist and thinks about probability, I measure this one, I change my attitude about something far away. This is action at a distance.
All right, so we're going to have to move on. There are a couple more questions. I saw that Aurelian has a question for Dave Chalmers, but if it's all right, I had a question for Vanessa. So I apologize if this is, I don't know that this was asked precisely in this way before, but I apologize if it was. So it seems like there are two main issues at play in your work. One is a question of practice. You know, is quantum mechanics able to account for what we actually go out and see? Is quantum mechanics capable of predicting and explaining phenomena that we go out and measure in chemistry or not? Or are there simply laws in chemistry that do not supervene on presumably or supposedly underlying laws of physics and quantum mechanics in particular. And that's an empirical question. And then there's a second question, which is, to what degree do different resolutions of the measurement problem answer an in principle question, which is the question of, when and how do molecules have, the particular structures that they do. Do I have that characterization right?
Yes, to an extent, yes, I think so.
Okay, yeah, so I guess my question is, to the extent that all the different interpretive frameworks, talk about small isolated systems evolving unitarily, systems that are in, some degree of contact with environmental degrees of freedom or measurement devices or whatever, experience something like a decoherence, whether it's just decoherence alone or whether there's also a physical collapse that takes place once enough, degrees of freedom of the environment are entangled with it. But what they also all agree on, they have to, is that observers perceive definite outcomes, whether those outcomes are truly, single outcomes or in a Everettian sense, they're not, but certainly observers perceive definite outcomes. So to the extent that really any interpretive or theory of quantum mechanics that attempts to resolve the measurement problem, to the extent that they all basically agree on that, I guess my question is, how does that interface with the first side of the question about whether quantum mechanics is able to account for, what we actually observe experimentally when we ask to look at or in some way measure molecular structure? Or is or is it just a question that the interpretations will differ on when and in what way those molecular structures actually occur? I guess what I'm trying to ask is, do they, regardless of one's particular choice of interpretation for quantum mechanics, as long as they agree on those basic features of the theory, are they all going to predict that when we go out and look at a molecule, we will perceive that it has a definite molecular structure?
Yes, I would think so. Yes, in non-isolation, of course, they would have to comply with the empirical evidence, right?
Right.
But there is an interesting thing here. It seems that there is too strong of an expectation to solve everything by the measurement problem. And there is also too strong of an expectation from reduction itself, right? So in order for reduction to be convincing, we will have to have a form of quantum mechanics that can give us everything, chemically speaking, which I don't see why this has to be the case, right? And neither does molecular structure has to solve everything, even the in principle and the in practice problems, in order to say that, we have a reductive relation between the two sciences. And let me give you an example of this. So suppose we find out which interpretation is correct, and we know how the measurement problem is solved, and how our description is compliant with our empirical observations and so forth. Still, the practical issues stand, and one of them, for example, is how do you derive chemical bonds from quantum mechanics? Now, this has nothing to do with the measurement problem, and it's in large part a conceptual issue as well, and an epistemological one, to the extent that, as Alex said before, there are a lot of approximations and idealizations made in the conceptual analysis of chemical properties, right? So, and this is a very complicated issue, in part because chemistry is in large part not a mathematical science. So chemistry doesn't explain chemical phenomena merely by mathematics and equations. So the connection with quantum mechanics cannot be built in a straightforward manner. And there are bound to be some sort of tails within chemistry that we're going to fail to kind of connect in a straightforward way with quantum mechanics. But from there to go to the jump that there's something about chemical entities that is not determined or is not supervenient on physical stuff, I think is too big of a jump, right? And I don't see where the empirical evidence of this comes forward. So when they ask me such questions, I want to turn this around and say, okay, so what empirical evidence do you have then that chemical entities are over and above and independent of physical stuff? And I don't think there are, especially if you look at how much quantum mechanics has contributed to our understanding of chemical entities. So even with respect to chemical bonds, right, and molecular structure, chemists have gained so much insight by by finding out the effects of delocalization in the stability of molecules, in the stability of certain structures, right? So even in its complete form, and even when we don't have all the answers of how quantum mechanics accommodates chemical phenomena, it is, at least for me, it's quite convincing that it has contributed to such an extent that surely there has to be a dependence relation between the two, a strong dependence relation.
Thank you. That clarifies things. If I could just maybe add one more item to this. So one very oversimplified way to think about the measurement problem is, why do we perceive definite outcomes? Yeah. Right? And it could be because there are definite outcomes, or there are not, but somehow there's some mechanism which we perceive them. If, to the extent that there is a solution to the measurement problem, there's an answer to the question of why we perceive definite outcomes. If we don't have an answer to the measurement problem, or there is no answer, or it's a fundamental problem, then there are all kinds of problems throughout our experience of the world, right? If we cannot account for why we perceive definite outcomes, all kinds of stuff breaks down. To the extent that we believe either that there isn't truly a measurement problem, or that there is, but some interpretation resolves it, and there is some explanation for why we perceive definite outcomes, well, then a lot of problems in the world, go away. And so it is what you're trying to argue, that among those problems in the world that are sensitive to whether or not we have some claimed solution to the measurement problem, the problem of why we perceive definite outcomes, that among those are these problems, a small set of problems in chemistry, or not a particular set of problems in chemistry, perhaps I should say. That's the argument being made here. The chemistry is not immune from the set of things that would be problematic if we don't have a way to account for the perception of definite outcomes. Okay, yeah, that clarifies things a lot for me. Thank you very much. Okay.
Can I say something on that?
Please, go ahead, please.
Even in that case, this shows that this problem is not unique to chemistry, right? And if it does have a solution, it's going to be probably a physical one in order to accommodate the universality of this problem, right?
Right. Good. That's very clarifying. Thank you so much. All right. So I have a question from Aurelian, and then I have one from Lev, and then Simon and Rob, depending on time. But we only have 4 minutes, and I do want to make sure we end on time. So Aurelian, please go ahead. I think you had a question for Dave.
Okay, so thank you. So my question is, in the chat, we had a discussion about the role of decoherence concerning in the brain process. And I wanted simply to ask this question in order that maybe you can say something about that, because for me, the question was about the fact that the decoherence is so fast that it's competing with any process of spontaneous collapse or continuous collapse or whatever. And I would like to know what you think about this, what you wrote about this computer story. You would like to make a test with quantum computer, and maybe you can comment a bit.
Yeah, like I said in the chat, I think decoherence is a positive for us. Yeah, decoherence is going to lead to the brain very naturally evolving into a superposition of quasi-classical states quite soon, which is great, which means they're ripe for collapse. So yeah, decoherence organizes us into a bunch of into a superposition of the relevant states, and then collapse selects one. Of course, it's going to depend what the locus is of collapse. If it's ultra low level, then maybe collapse will happen before that, or that decoherence takes place. I'm inclined to think that more plausible theories here might bring in collapse at a higher level, in which case collapse and decoherence will work very well together.
All right, so Lev, and then Rob. I'm sorry, I didn't realize that the chat you'd said you'd had a finger on the earlier discussion. Did you want to?
Well, it was for Vanessa, but you sort of wandered in your second question. You wandered away from my finger.
Well, that's
So
okay. We can come back.
Okay. Well, I mean, I wanted to get a sense from Vanessa to the extent to which she thinks that chemistry is in principle reducible to physics, or whether you're stuck with some form of emergence, and if so, what you mean by emergence.
And what you mean by reduction as well, right?
Well, you use the term. You use the term. So,
but this also gets to my question too, whether it's a merely empirical reduction or something stronger. But go on.
Yes, this is a difficult question because you can define reduction and emergence in many different ways. And if I were to give like a short answer, I would say, in some ways, I believe there is reduction. In other senses of that word, I believe there is not reduction. And there's some senses of emergence that I believe there is emergence, and other ways of emergence that I don't believe in.
Let's start with supervenience then. Whether, I mean, some people believe you don't have, you can have a failure of reduction and yet have supervenience.
Yes, that is true. And I also believe that supervenience is correct in the sense that whenever there's a change in the chemical level, there's always going to be a corresponding change in the physical level as well. And this doesn't require reduction in the sense of having a derivation, a strict derivation of the higher level from the physical level. So I wouldn't require this form of reduction.
Okay, so does supervenience preclude emergence? Or can you have emergence with supervenience because you don't know how to explain the higher level phenomenon from the lower level phenomena?
Yes, okay, very good question. I believe there are certain forms of emergence that are incompatible with the acceptance of supervenience. And I've actually written about this with respect to the strong emergence of molecular structure, because I take the evidence that is employed for the strong emergence of molecular structure to also be suggestive of the rejection of emergence. So it seems that the two have to be incompatible, at least in its current form. However, as I said in the presentation as well, to the extent that you can provide an emergentist account in the context of a particular interpretation, I don't see why you can't have some account of emergence which is compatible with the supervenience, a weak form of emergence. But if you are to defend a form of emergence that is stronger than that, so an emergence of chemical entities at the level of ontology that is distinct and in a substantial way independent from the physical stuff, I don't really believe in that sort of emergence, to be honest.
So unfortunately, we're going to have to end things there because we are just at time, and I want to be respectful of everybody's need to get to where they're going next. But I want to thank all three of our speakers for truly wonderful and really deeply interesting talks. So thanks again so much.
Thank you very much.
And I want to thank everybody who participated. You have all asked very interesting questions. I know I've learned a lot. Just as a reminder, the talks will be posted to the YouTube channel very soon, so you can go back and look at them. And also stay tuned for an announcement for the next mini workshop in this series, which will be the 15th. I hope all of you are staying safe and are doing well and are having an okay summer. It's good to see everybody.
Thank you very much, Jacob. Thank you very much.
Organized.
Bye all.
And you are good. I like you.
Bye. Thank you very much.
I just hope that one day we'll be able to do something like this in person, but we'll see.
Okay.